Now we present the basic mechanical devices called simple machines, which are used to do work with reduced effort and energy through a mechanical advantage. We start a more general classification of mechanical devices by dividing them into two groups. Power machines or prime movers convert some form of energy into another form of energy that is more useful for a given purpose. Power machines are, for example, hydraulic motors converting hydraulic pressure into mechanical energy, steam engines converting heat into mechanical energy, dynamos converting mechanical energy into electric generators also converting mechanical energy into electric energy, or electric motors converting electric energy into mechanical energy. The counterpart of power machines are working machines designed to perform useful work while consuming energy provided by power machines or simply muscle force. Typical examples for work machines are machine tools designed to form or cut parts made of metal or other rigid materials, cranes used to lift heavy objects or to move them horizontally, bicycles which are pedal or motor powered, two-wheeled steerable single-track vehicles, or sewing machines used to stitch materials with thread and powered by treadle or electricity. Working machines have several basic types called simple machines, which are essentially the building blocks of more complex machines. As their name shows, simple machines are mechanical devices with or without few moving parts. They are used to alter the direction and the magnitude of forces applied on them, functioning as force multipliers to do work. As a result, they reduce the effort and energy consumption through a mechanical advantage. Simple machines can be divided into two groups as well. Lever-like machines belong to the first group, whereas the second group consists of machines using inclined planes. Lever-like machines are lever, wheel and axle, and pulley, each of them used to reduce the amount of force needed to lift or lower a load. Machines using inclined plane are inclined planes or ramps, also applied to reduce the force necessary to overcome the force of gravity when elevating or lowering a heavy object, wedges used for separating two objects or the parts of a single object, lifting loads, or tightening objects to hold them in place, and screws used either as a fastener to hold objects together or as a force modifier. We will discuss the different types of the simple machines in these two groups, but first we make some statements on the operation of simple machines in general. Usually, two unconstrained forces are applied on a simple machine. The first one is called the effort and represented by the force F, which can, for example, be a muscular force. The second force is known as the load, represented by the weight G. If we neglect the friction between the parts of a simple machine or the elasticity of the parts, that is, we consider them rigid bodies, then we talk about ideal machines. We will determine when ideal machines are in equilibrium under the instantaneous influence of the effort and the load. The force somewhat greater than the effort corresponding the equilibrium of the ideal machine is already enough to do the work with the machine, for example to lift a load. However, in practice we often need much greater force to do work due to the friction neglected in the case of ideal machines. Before determining the equilibrium conditions for ideal machines, we will examine some general properties of these machines. If the muscle force F1 is applied on a lever to lift a body without acceleration, then the body of weight G is directly lifted by the force F2 equal to minus the weight G of the body. The effort F2 exerted on the body by the lever is enough to overcome the load G. In this sense, we can talk about transferring force from one body to another one, here from the lever to the body placed on the beam of the lever, that is, simple machines are used for transferring force. The magnitude and the direction of the input force F1 applied on the machine can be different from those of the output force F2. The practical use of simple machines already recognized in ancient times is just that a force can be used to overcome a greater load with their help. However, according to the law of conservation of energy, the work done by the output force F2 cannot be greater than the work done by the input force F1 in the same time. In other words, the useful work W2 done by the machine cannot be greater than the work W1 done on the machine by the effort. Simple machines can reduce the effort required to do the work but cannot change the work done. In order to do the same amount of work, we need apply a smaller force over a longer distance. In the case of non-ideal machines, friction must be taken into account, and the work W2 is less than the work W1 because some amount of the input force converted into frictional work instead of useful work. Then the efficiency eta of a simple machine is given by the ratio of the useful work W2 to the input work W1, which is equal to the ratio of the useful power P2 to the input power P1. In the ideal case, the efficiency eta is equal to 1, or 100%, otherwise it is always less than 1. Let us start the discussion on lever-type machines with the lever itself. A lever is simply a rigid beam that is free to rotate about an axis. Specifically, a lever transmits and modifies force or motion when forces are applied at 2 points of its beam and it turns about a third one on a fulcrum. It is used to exert a pressure or sustain a load G at one point of the beam by the application of a force or effort F at a second point turning about its axis of rotation on a fulcrum. We consider such levers where the unconstrained forces applied on the beam are only the effort F and the load G acting in the plane or planes perpendicular to the axis of rotation. Based on the positions of the lines of action of the effort F and the load G relative to the fulcrum, we distinguish three orders or classes of levers. A lever that has the fulcrum O between the lines of action of the load G and the effort F as seen in the example, is known as a first order or first class lever. In the case of a second order or second class lever, the line of action of the load G is between the fulcrum O and the line of action of the effort F, as seen in the second example. A third order or third class lever has the line of action of the effort F between the fulcrum O and the line of action of the load G, as in the case of the human forearm depicted in this figure. We have already determined the general condition of the balance of a system of forces acting on a rigid body. We demonstrated that the rigid body is in equilibrium if the vector sum of the torques produced by the forces with respect to an axis of rotation vanishes. A special case of this condition with two forces acting on a beam free to rotate was formulated by the lever principle. By applying the lever principle for all the three classes of levers, we can state that the magnitude of the effort F times the lever arm dF of the force F is equal to the magnitude of the load G times the lever arm dG, or the ratio of G to F is equal to the ratio of dF to dG. This ratio, that is the ratio of the magnitude of the load or the output force produced by the lever to the magnitude to the effort or the input force applied on the lever, is called the mechanical advantage of the lever, or in generally the mechanical advantage of any simple machine. Then the lever principle shows that levers convert a small force applied over a long distance to a large force applied over a small distance. In the example illustrating second-order levers, the axis O of rotation is fixed, that is, the fulcrum is always at the end of the beam on the ground. In the case of the first-order lever shown here, the position of the axis of rotation changes along the curved crowbar with rising or lowering the right end of the crowbar. However, we can always replace the instantaneous axis of rotation with a fixed imaginary axis at a given instance of time, and determine the condition of equilibrium of the lever. In the case of the human forearm, since the bicipital muscle or biceps exerts the force F close to the axis of rotation O, the lever arm of the muscular force F is smaller than the lever arm of the load G. As a result, the effort F is much greater than the load G and our arm can move faster over a longer distance. Besides the crowbars shown in these figures, there are many other applications of the lever, such as scissors, pincers, nutcrackers, oars, wheelbarrows, railway crossing gates, various balance scales and so on. The second type of lever-like machines is the wheel and axle. As its name shows, this simple machine consists of an axle or a cylindrical drum to which a wheel is fastened such that the wheel is concentric with the axle or the drum. Sometimes the wheel is replaced with a lever. If a force F is applied to the wheel by unwinding a rope or chain from it, then the torque produced by the force turns the axle around which another rope or chain is wound. The load G suspended from the axle can be lifted by applying a sufficient effort F. The lines of action of the effort F and the load G correspond to the tangents of the wheel of radius RF and the axle of radius RG, respectively. Let us suppose that the wheel and axle is in equilibrium, that is, the forces acting on it are balanced. Then the net torque produced by the forces F and G vanishes, and we can write that the magnitude of the force F times its lever arm RF is equal to the magnitude of the force G times its lever arm RG. That is, the ratio of G to F is equal to the ratio of RF to RG, which is greater than 1. This result shows that a wheel and axle provides a mechanical advantage equal to the ratio of the diameter of the wheel to that of the axle. Let us consider now a gear, or cogwheel, which is just a wheel and axle with teeth or cogs. In the figure we present the operation of two interlocking cogwheels, where we can see that the lever arm of the load G is given by the radius dG of the axle fastened to the driven gear of radius RG. The effort F applied on the arm fastened to the driver gear of radius RF has the lever arm dF given by the length of the arm. Here the radii of the cogwheels are the radii of their circumferential pitch or pitch circle. Then the ratio of dF to RF times the force F is transmitted from the driver gear to the driven one at the interlocking point. Similarly, the ratio of dG to RG times the force G is transmitted from the greater gear to the smaller one at the interlocking point. Here the transmitted forces are tangent to the cogwheels and have opposite direction. In equilibrium, the net force exerted at the interlocking point vanishes, and we can write that the magnitude of the force F times the ratio of dF to RF is equal to the magnitude of the force G times the ratio of dG to RG. Then the ratio of G to F is given by the ratio of dF to dG, times the ratio of Rg to Rf. If the lever arms dg and df are equal, then the ratio of the load to the effort is equal to the ratio of the radii of the cogwheels. Since one rotation of any gear is given by the circumference of its pitch circle, that is 2 pi times its radius, the ratio of g to f is also equal to the gear ratio, that is the ratio of the number of rotations of the driver gear to the number of rotations of the driven gear. The latter can also be expressed as the ratio of the number of teeth of the driven gear to the number of teeth of the driver gear. Then we can conclude that the mechanical advantage of interlocking gears is equal to their gear ratio. The third type of lever-like machines is the pulley used in different kinds of arrangements. The first type of arrangement is the fixed pulley seen in the figure. If we pass a rope transmitting forces over a fixed pulley, then the fixed pulley can change the direction of the line of action of the force applied on the end of the rope. In equilibrium, the magnitude of the effort F applied on one end of the rope passing over the pulley is equal to the magnitude of the load G suspended from its other end. This statement follows from the condition of the vanishing net torque produced by the forces F and G, that is the magnitude of the effort F times its lever arm R, minus the magnitude of the load G times its lever arm R is equal to 0. Here the lever arm R is given by the radius of the pulley. We can also obtain this result by applying the principle of virtual work. For the displacement delta S of the end of the rope in the direction of the force F, the height of the load G is increased by delta S if the rope cannot be stretched. Then the virtual work can be written as the magnitude of the force F times the length of delta S, minus the magnitude of the force G times the length of delta S, which must vanish. This also gives the equality of the magnitudes of F and G. A second kind of arrangements of pulleys is the movable pulley shown here. A movable pulley can be considered as a second-class lever, where the axis of rotation passes through the point O at which the rope enters the pulley. The lever arm of the effort F with respect to the point O is given by 2 times the radius R of the pulley. The lever arm of the load G with respect to the point O is equal to the radius R. Then the equilibrium condition of the vanishing net torque gives the equation stating that the magnitude of the force F times 2 times the radius R, minus the magnitude of the force G times the radius R is equal to 0. As a result, the magnitude of the effort F is given by the magnitude of the load G over 2. In other words, if the two ends of the rope wound around a movable pulley are parallel and the forces acting on the pulley are in balance, then the effort F is just the half of the load G, producing the mechanical advantage of 2. Here the weight of the pulley and the rope is included in the load G. Normally, movable pulleys are applied with fixed one, as seen in the figure. When more pulleys are combined with ropes or cables into one system, we talk about a combined pulley called a block and tackle. The block and tackle depicted in the figure consists of 2 fixed pulleys and 2 movable ones, where each pair has a common fork. Let us consider the end of the rope at the point of action of the effort F. For any displacement delta S of the end of the rope in the direction of F, the elevation of the point of action of the load G is equal to delta S over 4. Then the principle of virtual work states that the magnitude of the force F times the length of the displacement delta S, minus the magnitude of the force G times the length of the displacement delta S over 4 is equal to 0. As a result, the magnitude of the effort F is equal to the magnitude of the load G over 4, which is the force exerted on each of the 4 ropes connecting the pulleys in the block and tackle. For a block and tackle of 2 times N pulleys, the magnitude of the effort F is given by the magnitude of the load G over 2 times N in equilibrium, and its mechanical advantage is given by 2 times N. Since the effect of the friction between the ropes or cables and the pulleys increases with the number of the pulleys, there is a reasonable upper limit for the number of the pulleys applied in a block and tackle. Another type of arrangement of pulleys is the differential pulley shown here. A differential pulley is a tackle that consists of the following parts. An upper block with 2 fixed pulleys of radii R and are attached together such that they rotate about the same axis, a movable single lower pulley that carries the load G, and an endless cable or chain that passes around all the pulleys and hangs in a loop for operating the mechanism by applying the effort F on it. The fixed pulleys are toothed to avoid slippage of the chain. If the load G is applied on the movable pulley, it is also exerted on both sides of the loop. As a result, the forces F and G over 2 are applied with the lever arms R and are on the fixed pulleys turning them clockwise, and at the same time the force G over 2 is applied on the pulley of radius R turning it counterclockwise. Then the condition of the equilibrium for the vanishing net torque states that the magnitude of the force F times the radius R, plus the magnitude of the force G over 2 times the radius R, minus the magnitude of the force G over 2 times the radius R is equal to 0. By expressing the effort F from this equation, we can write it as the load G times the ratio of R minus R to 2 times R. The mechanical advantage given by the ratio of F to G is equal to 2 divided by 1 minus the ratio of the radius r to the radius capital R. For example, if the ratio of r to capital R is equal to 0.8, then the effort F can be the tenth of the load G. Now we present the simple machines using inclined planes. The first kind of them is the inclined plane itself. In the usual application of inclined planes, the line of action of the force F is either parallel with the inclined plane or it has a horizontal direction. If the direction of the force F is parallel with the inclined plane, then the condition of equilibrium is the balance of the force F and the load G representing the weight of the cart on the ramp. The force minus F exerted on the cart keeps it in equilibrium, provided minus F is the projection of the weight G on the line of action of F. Then the condition of equilibrium is given by the equation stating that the magnitude of the effort F is equal to the magnitude of the load G, times the sine of the inclination angle alpha of the ramp. If the direction of the force F is horizontal, then the condition of equilibrium demands that the projection of the effort F on the plane parallel with the inclined plane, that is F divided by sine alpha, and the projection of the weight G have the same length, but point in opposite directions. This gives the relation stating that the magnitude of the effort F times cosine alpha is equal to the magnitude of the weight G times sine alpha. As a result, the condition of equilibrium is given by the equation stating that the magnitude of the effort F is given by the magnitude of the load G times tangent alpha. These two cases show that the mechanical advantage of an inclined plane is either equal to the reciprocal of the sine of its inclination angle alpha, or the cotangent of the angle alpha. The second kind of simple machines presented here is the wedge. A wedge with a symmetric shape is made up of two inclined planes as shown here. If alpha is the wedge angle, then the inclination angle of both the inclined planes is equal to alpha over 2. Here the letters L and W denote the length of the sloping faces and the width of the blunt end of the wedge, respectively. In many applications of a wedge, for example, knife, axe, nail, pin and so on, the load is given by the forces G1 and G2 perpendicular to the sloping faces of the wedge with the same magnitude G, whereas the effort F is perpendicular to the blunt end of the wedge. In equilibrium the three forces are balanced, and the condition of equilibrium for a symmetric wedge is given by the equation stating that the magnitude of the force F is equal to 2 times the magnitude G, times the sine of the angle alpha over 2. This condition can also be derived from the fact that the effort F over 2 and the loads G1 and G2 are exerted on each inclined planes, where the effort is parallel of the base of the inclined planes and the loads are perpendicular to the inclined planes. Then the figure in the right-hand side shows that the magnitude of the force F over 2 is equal to the magnitude G times the sine of alpha over 2 in equilibrium. Since sine alpha over 2 can be expressed as the ratio of the width W of the blunt end to 2 times the length L of the sloping faces, the mechanical advantage of the symmetric wedge is equal to the ratio of the width W of its blunt end to the length L of its sloping faces. The third kind of simple machines presented here is the screw. A screw is basically an inclined plane wrapped around a cylinder to form a helical thread, as seen in the figure. For a cylinder of height h and radius r, the length of the base of the inclined plane is given by the circumference 2 pi times r of the cylinder, whereas h is the thread pitch of the screw. A typical lifting device utilizing the mechanical advantage of a screw thread is a screw jack used to lift a load by converting the rotation of a screw into vertical motion. If a load G is lifted or a body is pressed by a force G, then the line of action of the force G is the axis of the screw and the effort F is applied along the tangent to the circumference of the screw. The force G is perpendicular to the base of the inclined plane wrapped around the screw and the force F is parallel with the base. As a result, the condition of equilibrium states that the magnitude of the effort F is given by the magnitude of the force G times the tangent of the inclination angle alpha. Since the right-hand side is equal to G times the ratio of the thread pitch h to 2 pi times the radius r, the mechanical advantage of a screw jack is given by the ratio of the thread pitch of its screw to the circumference of the screw. In the case of a differential screw jack, the line of action of the force F is not the tangent to the circumference of the screw, but F is applied on the end of the jack arm of length L. As a result, the torque produced by the effort F is not given by the magnitude of F times the radius r of the screw, but the magnitude of F times the length L of the lever arm. We can apply the principle of virtual work for a differential screw jack as follows. If the effort F turning the screw rotates it by the angle delta phi, then the work done by the force F is equal to the magnitude of the F times the length L of its lever arm times the angle delta phi. The work done by the load G is equal to minus the magnitude of G times the elevation of the screw. Here the elevation is given by the thread pitch h times delta phi over 2 pi, since the elevation for a complete turn of the screw determined by the angle 2 pi is equal to h. The principle of virtual work tells us that the net work done by the forces F and G along the virtual displacement delta phi must vanish. If we factor out delta phi in the left-hand side of the equation, we obtain the equation for the condition of equilibrium stating that the mechanical advantage of a screw jack is equal to the ratio of its thread pitch h to 2 pi times the length L of the jack arm. This expression can also be written as the thread pitch h over 2 pi times the radius r, times the ratio of the radius r to the length L of the jack arm. Since the ratio of 2 pi times L to h can be chosen great enough, screw jacks can produce huge lifting force even if the friction of the screw increases with the ratio of 2 pi times r to h. For example, if the thread pitch is equal to 2 mm, the length L of the jack arm is equal to 50 cm and the efficiency of the screw jack is equal to 50%, then the load can be the ratio of 0.5 times 2 pi times 50 to 0.2 times F, that is about 800 times the effort.